Do we all have this one? Okay, back to concepts and pictures, away from tedious code. Can we get an amen on that? Yes. So the rest of the course is transitioning into what most people would consider proper structural equation modeling. Once you have more than one latent variable and they're connected in some sort of meaningful way, I think that's when people would start using that terminology. But it is somewhat author specific. So I am adding to what we're doing in terms of structural models in this set of slides, as well as trying to provide some guidance in practice as to when you would do things different ways. Because from this point, there's not necessarily a right answer. There's only what is reasonable and useful given the research questions and the context that you're trying to analyze. So higher order factor models, which I know several of you have structures that were intended to look like that, as well as what are known as method factors or bifactor models. We've talked a little bit about this, and I wanted to do a more in-depth treatment. So big picture first, sequence of steps. So when you're approaching a measurement problem, the first thing that we would want to do is tackle the measurement model portion. Don't worry about how the factors are related until you worry about whether each factor is actually behaving in the way that you intended with respect to its indicators. So how many factors do you need? Which items are they predicting reliably? And whether we need any additional sources of multidimensionality in terms of additional factors or error covariances. So for models that have lots of items, I would start per factor. So anytime that you have at least 4 indicators per factor, I would fit separate models for each factor first, because trying to troubleshoot a giant matrix is going to be much more challenging than troubleshooting it in pieces. So the logic is that if you know that each factor fits by itself, and you put all the factors together in one larger model and it doesn't fit, you can be reasonably sure that the reason it doesn't fit is because of cross-factor item residual relationships. So if everything within a factor is good and it doesn't fit when you put it together, it has to be this item on this factor is more related to this item on this other factor, not anything that's inside. So it cuts down on the logical possibilities as to what would go wrong if you sort of break the analysis into pieces. So for each factor, I would assess global model fit. I would try to assess local model fit. Whether or not I have global fit, I would also still look at these local mispredicted relationships, and then try to get a sense as to how reliably each of the factors is measured. Once you are at this point where all of your measurement models are good enough, then you can consider the structural model and put all the factors together at the same time. So I have 2 different things that would be relevant under that, is to what extent are your factors consistent with the idea of a higher order factor, or a second order factor as it's called, and then how could we possibly use method or specific factors to address additional sources of covariance like wording or other kinds of commonalities. So that's the big picture here. So higher order factor models, they work the same way as factor models on items, but at the level of the factors as indicators. So if I have 3 factors, then I can have 3 covariances between them, right? I can do that. What if I think that my 3 factors are actually facets of some higher order factor? So I know a couple of you have this, right? Who has a higher order factor as part of their story? Do you? Maybe? Okay, what's yours? Remind me. Teacher goodness, I know that.
Yeah, so we have like a matrix where I've only been looking at the category that I think is the higher order category of authority, and then we have 3 categories that we think are related to that.
So authority, you said, is higher order, and then 3 things underneath it? Yep. I know there's at least 3 or 4 other people I've talked to about this, but the idea that you have sort of like subscales of a measure that are getting at, some overarching construct, and these are more specific variants of that, that's what we're doing. And in the same way that the job of a latent factor in the first place is to recreate the pattern of covariance among its indicators, the job of a higher order factor is to recreate the pattern of covariance among its lower order factors. It's exactly the same idea. So we're asking how well the pattern of covariance among my lower order factors can be recreated with a higher order factor. And a logical prerequisite to being able to answer this question is that you have covariances among your factors in the first place. So do you remember what I said about game over if your items aren't correlated? Like staring at a correlation matrix is step one, because if your items aren't correlated, it's not going to go well. Same thing here. If your factors aren't correlated, the higher order factor has nothing to do. So correlated lower order factors is the limiting condition on this. And at this point, when we talk about structural model considerations, the distinction of CFA versus IFA is gone. Lower order factors are continuous variables. They are multivariate, normally distributed in terms of how we try to estimate them by summarizing their means, variances, and covariances. So regardless of what kind of items you have, when you're talking about relationships among the factors, the traits themselves, it's like a CFA model in that sense. They're all continuous. And latent variables don't have means, and so those are going to fall out of the story. So we're only going to be worried about higher order factor variances and loadings of lower order factors onto those. So to start this process, we have to change the way that we identify the lower order factor models. In your homework 3 and in your homework 5, I had deliberately asked you to identify your models so that the factor means are all 0 and variances are 1. That way you know that a loading corresponds to a change that's a standard deviation, and your factor response plots are nice and easy because plus or minus 3 standard deviations is a reasonable thing for all of you. However, when your factor is going to become predicted, when it's going to be an outcome of a higher order factor, then its variance needs to become an estimated quantity because it needs to become left over after being predicted. So if you fix it to 1, that can break your model. So for that reason, this is the default method of estimation in both MPlus, Lavaan, and in most other SEM packages that I've been familiar with, where the first item's loading is fixed to 1, the factor variance is estimated instead. On the mean side, though, we keep it standardized. We estimate all item intercepts or thresholds and fix the factor mean to 0. So that means from this point forward, there's no additional information about the means that would be passed up in this. They're all concentrated on the item level. So this marker item method of identification will help you avoid convergence problems when your factors themselves turn into outcomes to be predicted. Okay, does that make sense? So I did. Okay. So here's what here's a option number 1 within the possibilities leading to a higher order factor model. So in this example, I have 3 factors, 3 different things. Each factor is measured by 4 items, and the first item for each of my factor has its loading fixed to 1. I am estimating all of the item intercepts or thresholds if this were an IFA underlying structure, as well as the factor means being fixed to 0, given that I've estimated all the intercepts. I would have error variances if this were a CFA model, not if it were an IFA model. And I have 3 estimated factor variances here. So then I have 3 possible covariances. So if we figure out what type of identification we have in terms of the measurement model versus the structural model, this is now a distinction that's important. For the measurement model, I have 12 items. So here's the formula for the number of possible degrees of freedom. I have 12 items times 12 plus 1 divided by 2. Plus the number of items again for the means. So 90 is the total degrees of freedom that I can have for the measurement model. I am going to spend 9 loadings, 12 intercepts, 12 residual variances for 33 in total. So 90 minus 33 is 57. So in terms of the measurement model, this is very, very much over-identified. So even though each of these is over-identified just by a little bit, like if I had 1 factor at a time with 4 indicators, that would only have 2 degrees of freedom. The combination has a lot of degrees of freedom left over because we're saying that the only reason why item 1 and item 5 are related is because of the covariance between factors 1 and 2. Likewise, the only reason why item 1 and item 12 are related is because of the covariance between factors 1 and 3. So a lot of room for misprediction in terms of how this model captures the relationships among these items. At the structural level, though, if we think about how many factor-related parameters we have, I have 0 potential factor means because I am estimating all the intercepts instead. I have 3 potential factor variances, and I have 3 potential factor covariances. If I estimate all of those, the structural model is just identified. Do you remember that vocabulary word, just identified? It means the model is estimable but not testable. So an alternative equivalent way of saying, hey, I have 3 factors and they're all correlated, is to say, no, 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 no. I have 3 factors and they're indicators of a higher order factor. Okay, let's do it that way. So forgive the change in the notation, but I'm running out of room on the slide and it's already too full. So I'm dropping the little curvy arrows because I'm running out of room here. So in this case, this thing up here is called a higher order factor or a second order factor. Take your pick. It is thought of as the reason why people have the scores on factor 1, 2, and 3 that they do. And factor 1 is the reason why people have the scores on items 1, 2, 3, and 4 that they do. So it's like this trickle-down system of expectations here. So the same measurement model is being fit as before. We still have 57 degrees of freedom left over for the measurement model. But for the structural model, I have replaced the covariances between the lower order factors with these higher order factor loadings. Okay, so that's a really important point. Covariances here, when there's no higher order factor, covariance is gone once you put it in. They are doing the same thing. So if you try to estimate a higher order factor and its loadings and still have all of the lower order factor covariances, that is redundant. The higher order factor loadings are inducing the correlations between the lower order factors. That is what they are doing. So for instance, if I had a standardized solution, I would say the correlation implied by the model between factor 1 and factor 2 is the loading for the higher order factor for factor 1 times the loading for the higher order factor for factor 2. In the same way that the expected correlations among the items are functions of their lower order loadings in the measurement model. It's the same. In terms of factor variances, these get a new vocabulary word. Factor variances are unconditional. They are what it would be if your factor is only a predictor. If your factor is itself an outcome of a higher order factor, then their variances become variance left over, variance that is not a higher order factor. And rather than call those error variances or residual variances, they call them disturbances. That's what the D stands for. Like there's a disturbance in the force. But factor variance left over that is not due to the higher order factor, that's the concept. Whatever factor 1 has that's not related to factors 2 and 3. Okay, any of that you need to hear again? People are writing things. I think that's a good sign. So unique variance for factor 1. Yeah, I can. So D1, disturbance 1, you can call that unique variance. Yeah, unique is good. Conceptually, it's error variance, but the term that people use is disturbance. So, in terms of parameters, we still have 6 possible because there's still 6 factor variances and 3 factor variances and 3 factor covariances. How we've gotten there, though, has changed. Rather than have 3 covariances directly among the lower order factors, now we have 3 loadings. That means that in order to identify the higher order factor, we have to fix its variance to 1. Rather than have 3 factor variances, as we had previously, now we have 3 leftover factor variances. Either way, 6 minus 6 is 0. The structural model is still just identified. So is this right? Can I say for 3 lower order factors that they are indicators of a higher order factor? Can I make that statement? What do you think? If I have 3 lower order factors and I fit a higher order factor like this, such that the structural model is just identified, do I have evidence that my lower order factors are consistent with the higher order factor? Say no? Why not? Because you can't test it. You can't be wrong. Exactly right. It's like six of one and half a dozen of the other. Have you heard that expression? This is literally what it is. 6 of one and half dozen of the other. A dozen is 12, unless it's a baker's dozen, which is 13. But I'm not a baker, so a dozen is 12 to me. So yeah, if this is your situation, you either have 3 covariances or you have 3 loadings. Model fits the same. And this is something that you will see in the literature be misunderstood quite frequently, because overall, this entire model is very much over-identified and testable. But with respect to how well the higher order factor fits its lower order factors, that part is just identified. So how many do I need to do this? If I have lower order factors and I want to test a higher order factor, how many lower order factors do I need to make my structural model testable? 4. Yeah, and you better try to have 5 so you have room to be wrong. Yep, 4. However, can you think of a way that I can cheat? What if we put constraints on these 3 factor loadings? Then we have room to be wrong. So if I fit what I might call a tau equivalent higher order factor, where all 3 loadings are equal to each other, then I save 2 degrees of freedom and then it is testable. So constraints could make it testable, but then you'd have to believe that all 3 lower order factors are equally good indicators of the higher order factor, which may not be the case. And here's one more possibility. Okay, watch carefully. Camera 1, camera 2. Camera 1, camera 2. What'd I change? Yeah, this is 1, and this factor variance is estimated. Is that going to change how it fits? Nope. It's just another way of identifying the higher order factor. Just depends on what you want the scale to be. Here's an example of higher order factors multiple. This is slide 8 from your textbook. So in this example, we have 4 lower order factors, 2 higher order factors. Each of the lower order factors is under-identified, but it becomes over-identified as a whole so long as this covariance between the 2 higher order factors is not 0. So it's the exact same concept as when you have 2 and 2 for your lower order factors. It is only over-identified and solvable if you have a covariance linking them together, because otherwise this would not stand on its own. So you don't have to have just a single higher order factor. It might make sense to have more than 1. So in this case, the structural model would have 4 lower order factors. So that's 4 times 5 for the number of variances and covariances divided by 2, plus 0 for the factor means because there aren't any, because all of the item intercepts would have been estimated instead. So if we were to estimate 4 leftover variances and 4 loadings and 1 covariance, then that's the 9, we have 1. So 1 degree of freedom allows us to be wrong just a tiny bit in terms of demonstrating fit of this higher order structure. So yes, the rules are the same. It just depends on how many factors you have. So if you have 2 lower order factors, you have 1 covariance between them. You can try to put a higher order factor onto that, but the loadings would have to be held equal for it to even work. And in that case, it doesn't often make a lot of sense to do that. Only if the 2 factors were super highly correlated might you consider doing that, because otherwise you're just taking the covariance and putting a circle around it and giving it a name. Question from the Zoomers, can you cross-load items onto multiple factors? Yes, you can, but not too many or it starts to break down. Generally speaking, in this world, people seek to avoid cross-loadings if possible because it muddies the interpretation as to what the factors are, especially if you want to have unique prediction of things from the factors. Then if they're partially reflecting the same items, that gets to be conceptually ambiguous. Does that help? Typing. Thumbs, okay, yes. See, I wish the Zoom chat could see dots, like, you know, when you're sending someone a text, you know they're replying to you. Like, but we don't have that. So, hey, Zoom developers, give me some dots in the next version. My Zoom wants to update itself like every other day, so you'd think that, you know, they're continually developing itself. 3 measurement model factors just identified. You can get it done, but you can't test fit. 4 meets over-identified, and then you can estimate and test. So how do we go through this process? If we have 4 or more subscale factors, then we have to create our own version of a saturated model to test the fit of the structural model specifically. So the fit of the overall model is not relevant at this stage. It is the fit difference between a saturated structural model and the one that you want. So a saturated structural model would have all factor covariances and variances just be estimated, right? That is the exact relationships among the factors. That's your new answer key with respect to how your structural model fits. So for instance, if I have 4, then I have 4 variances and 6 covariances that are possible. I can replace those with 4 disturbance variances and 4 loadings for a savings of 2. So then the question would be, relative to just letting all the factors covary how they want, is a model in which we say the covariance is due just to the factor loadings of the higher order factor, is that worse? So it is exactly the same concept as what we did at the item level, just at a higher factor level instead. If you have 3 or fewer, then we cannot be determined. It is also possible to have multiple higher order factors, as I said on the previous slide. And here is a former student's dissertation. Hi, Kelly. Giving you a shout out here. She thought that she had a higher order factor of something called school readiness at age 5 that she wanted to examine predictors of and outcomes of in a ginormous structural equation model. And yes, yeah, thank you, Kendall. I know you know Kelly. So yes, hi, Kelly. She graduated. Her dissertation is the done kind. So I don't even remember if her hypotheses were supported, but it doesn't matter, because once you do what you said, you're out, okay? Best dissertation is the done kind. But her indicators were approach to learning, math knowledge, language knowledge. These are all like subscales that had multiple items underneath them. And then social competence, emotional competence, and behavioral regulation. And I looked at her her models like initially when she went down this, and I'm like, I'm going to tell you this is not one factor. Like as a parent, I can tell you 100 that knowing your letters and being like academically ready to attend kindergarten and then keeping your shit together all day long are completely different skills. Can I get an amen? Amen. Yeah, any other elementary school teachers in here want to give me an amen on that one? Yeah. Yeah, my son is a great example, right? He got kicked out of preschool on a couple of occasions because he couldn't calm down after being aggrieved for something, right? He holds a grudge. So the fact that he, you know, knew all his numbers and his letters and could sign his name was not going to help him with the emotional regulation side of the puzzle. So it turned out that she had 2 higher order factors. And so everywhere in her research questions and hypotheses, she had to adjust to talk about academic versus non-academic school readiness, and it turned out they did have different relationships to other things. So you're not stuck with just one higher order factor. You can have as many as is theoretically motivated to you. The key to this, though, is to make sure that you are comparing against the right benchmark, which is a saturated structural model where all the covariances get to be what they want. Then you can see if your higher order factor accurately reproduces those in terms of model fit. Okay, how are we doing? A lot of words, but not new ideas. Question from the Zoomers, go for it.
So could you please repeat about the saturated baseline versus the alternative?
Yep.
So the first one, all 6 factor covariances. Then if you estimate a single higher order factor, then can it fit differently?
It can fit worse.
Okay.
So,
Okay. Oh,
yeah,
that
so,
makes sense.
yeah, if you have 4, then in terms of like information going in with which to estimate the structural model, you have 4 factor variances, you have 6 factor covariances, you do not have any factor means because they're all down at the item level and they don't get pushed up. So then the question is, let me phrase it there, are my 6 covariances among my lower order factors accurately represented by 4 higher order factor loadings? That's what it boils down to. It's a match of covariances to loadings, but it's not lower order, it's higher order. But that saves 2 degrees of freedom, so your model can fit worse or not worse because it is a simplification of the 6 covariances into 4 loadings.
Oh, I understand. Okay, thank you.
Yep, and in the same way that we did with the original measurement models. So like visually, the saturated version would be this version. So you're just letting all the factor covariances be whatever they would be. And you would want a matrix of that actually as like literally what your model prediction is as the right answer. And Tech4 is a piece of M+ output that will give that to you directly. And then you could compare it to a model that would look like this instead, where the factor covariances among the lower order factors are replaced with higher order factor loadings. And in this case, because there's only 3, there's 3 covariances or 3 loadings, it's the same damn thing. Once you get to 4, then there's 6 covariances versus 4 loadings. Once you get to 5, there's 10 versus 5, and it goes on from there. And yes, I do have an example. So we are going to go through this process with real data from a former student who was nice enough to lend it to me a long time ago. Okay, other questions? All right, so then in practice, when would you do this and when would it not be helpful to you? It depends on 2 things to me. The role of your higher order factor in the overall model you're trying to eventually get to, and the pattern of correlation among the lower order factors. So in this example, I have a box of some other predictor. It could be an observed variable or it could be a latent variable, doesn't really matter to my point. If this is what I want to do, is think about my factors as indicators of a higher order factor, then I would say this version of it is not that useful. Why not just have the predictor predict each of these 3 outcomes directly? What you are saying essentially is like a constraint in that the predictor is supposed to have the same relationship with each of these 3 factors. The only difference would be how much of it gets there because of the differences in the loadings. So to me, this doesn't make a lot of sense. However, if we flip it around, now if my higher order factor is the predictor and I have downstream outcomes that I want to relate it to, this is more useful. Do you remember what you learned about correlated predictors way back in multiple regression? Is it good to have super highly correlated predictors in multiple regression? Generally not, right? People call that collinearity or multi-collinearity or all those things, all the way up to singularity, which means perfect correlation and something is broken. To the extent that your predictors are related, it gets harder and harder to figure out what their unique contribution is. That's how it is. So if I think about that in this context, if I have these 3 factors that are super highly related to each other, correlations of 0.8 or 0.9, and I have them each try to predict an outcome, they're going to fight against each other. I could very well have a situation where my outcome has a very high level of prediction, meaning like a high R-square value, but none of these 3 individually is significant. And then good luck explaining that. So if you think there's enough commonality in your lower order factors that it's more parsimonious and effective to represent that as a higher order factor and then let it do the work in predicting your outcome, to me this is a reasonable alternative. In either of these cases, though, I have a clear signal as to what I think this higher order factor would be because it's related to all 3 of my indicators in a strong fashion. These are standardized loadings. If I have something like this, this would give me pause no matter what my intent is to where I want to put the higher order factor. So these are standardized loadings of 0.2, almost 1, and 0.1. It's like, well, what do I call this thing? It's mostly factor 2 with just a little bit of help from the other 2. So at that point, I don't know that I would be comfortable interpreting the results because it is just factor 2 for all intents and purposes that's going to be doing the work here. And if you have something like this, I would not even bother. So if your standardized loadings, even if you have 3 lower order factors only, if they're that low, there's nothing in common. The higher order factor has no variance to it, functionally speaking. So even in cases where you don't have the capacity to test the fit, I would use the standardized loadings as a gauge as to how useful that higher order factor would be in representing the common variance to be predicted or to become a predictor. So this is the point at which reasonable people might disagree. This kind of higher order factor structure is often used to rescue a concept that is not supposed to be multidimensional, but it is. So if you really want to think about this as a single thing, then a higher order factor can conceptually allow you to do that. However, it is much more useful as a predictor than an outcome, and only useful to the extent that the standardized loadings support that interpretation. All right. 136. Can I tell you a quick story, and then I'll let you go? It's a true story, but it's relevant, I swear. So the theme of this story is, tell me you haven't read my dissertation without telling me you haven't read my dissertation. Okay, that's my theme. Here's my dissertation. It was a very long, arduous project that culminated in this big structural equation model. The point of the project was to look at how attention and vision uniquely predicted impairment in a driving simulator in older adults, and more explicitly to compare a new measure of attention that I had developed against current standards. So this was the model that I was most interested in. I have, and you're going to see this in the very last week of class, I've got an example that shows through all these results. I have age as a measured variable. I have visual impairment that is measured by 6 different indicators of acuity and contrast sensitivity. I have a measure of processing speed that I'm treating as perfectly observed because there's only one. I have my latent factor for driving impairment, which was indicated by various measures of performance in a driving simulator. And then I have the green boxes, which was the whole point of the story. So DSCAN stands for driver scan. It's the test that I developed to do this project. And my whole thing was, to what extent does this measure incrementally predict driving impairment over all this other stuff? Okay, that was my question. I had a faculty member who invited themselves onto my dissertation committee because they had expertise in structural equation modeling, and I spent 15 minutes during my defense arguing with this person as to whether I needed a latent factor of attention. Their point was that these things are really highly related to each other. They were correlated 0.5, 0.6, and they should be indicators of a latent factor. So riddle me this, folks. If I stuck a latent factor of attention here, and I had that latent factor predict driving impairment, could I have answered my research question about how well each of these things predicted uniquely? I would argue no. So eventually my chair shut down the discussion, but this person was unhappy with my response. Had they read my research questions in the term incremental prediction, I'm pretty sure they would have agreed with me, but that didn't happen. So, but I got out too. You can't take it away. That's right. Once you have it, it's yours. So no, I did not want a latent factor of attention. But to be fair, after having that discussion, I decided to go ahead and put 2 different models in the publication, one where it was and one where it wasn't, to try and hedge my bets. All right, that's a good transition point. So it is up to you whether you think a higher order factor is a useful thing. If you're interested in how the indicators of it predict things incrementally or uniquely, then a higher order factor is not useful. If you want to make use of their common information to try to get a better measure of whatever it is for your construct, then it would be useful. But it is dictated by the correlations among your factors and the goals of your analysis. How's that? Okay. Thumbs up from the Zoomers. Any other questions before we call it a week? And we'll pick this up next time. Nope. All right. Then let us know if you need anything. Homework 5 is due on Monday. I will be checking email tomorrow and over the weekend if you have any questions. Okay? Okay, then bye for now. See you next week. have good weekends. Thanks for being here.